Is the slide visible? Just I'm changing the slide. Can anyone respond, please? Good evening, everyone. So today we will be thoroughly go through the petrochemical industry. In earlier classes, we have learned about petroleum industry, their production, their occurrence, and other fractionation. What are the products we get from the petroleum refinery? We have discussed detailed in the previous classes. So in this class, we will be discussing about the petrochemical industry. So So we can see that crude petroleum that is refined to several useful fractions that we used atmospheric distillation. Last class we have discussed atmospheric distillation as well as vacuum distillation. So from their distillation or fractionation, we get lot of useful products, and those useful products are further processed like various steam cracking process or hydrogenation process. As per the requirement, we get by lot of other products. About 10% of the petroleum is used to prepare a range of chemical called petroleum. So based upon the crude fractions that we get from the petroleum industry, we further processed it, and the range of chemical we derived from the petroleum refinery feedstock, we call that petrochemical. So petrochemical as a group of chemicals, those are produced directly or indirectly from the hydrocarbons of petroleum or natural gas as well. A natural gas that is primarily methane. The gaseous hydrocarbons have found important use as a starting material to produce a large variety of the petrochemicals. Nowadays, the demand of the petrochemical and the material those are derived from the petrochemicals is so great that we need to deliberately convert the higher hydrocarbons that we get from the petroleum refinery after fractionation. We convert it to the smaller gaseous hydrocarbons by process of cracking. We do a lot of catalytic cracking, steam cracking, and other. We have discussed the petroleum refinery processes in the earlier classes. Products made from the petrochemicals include a lot of polymers like plastics, soaps, detergents, other solvents like toluene, benzene, ethanol, methanol, other solvents, drugs, fertilizer, pesticides, various explosives, synthetic fibers, rubbers, paints, insulating material, and others. So there are lot of chemicals that we derived from the uh, petroleum product as a feedstock. We are deriving a lot of chemicals. Those are all categorized as petrochemicals. Okay. So just now I have told that from the petroleum industry we distillate, we do the fractionation, and we get lot of product. And out of that product we get further, we do further processing or further chemical processing of those products, and we then produce petrochemical, a lot of chemicals, right? So what are the feedstock that we generally uh, feed into the petrochemical industry process unit? That is one natural gas which is largely content of methane. It is mostly major raw material that are used for petrochemical from the C1 chemicals. We get lot of other petrochemical product from the C1 or natural gas, and it also contained other than methane, it also contained ethane that is less than 4% in the natural gas, which is also a valuable product since ethylene can also be produced by thermal cracking of the ethane, right? However, most of the ethylene is coming from refinery gases. We directly get from the top product of the atmospheric distillation column. We also get refinery refinery gases, right? So there we also get natural gas, and from the natural gas we do other processing of ethane and those things, so we can get more valuable product, petrochemical product. Another one is the liquefied petroleum gas. Liquefied petroleum gas, that is also we get from the atmospheric distillation column, that is easily extracted from the natural gas and can be transported via tank cars or pipeline as a liquid. So it is very easy to transport. So it contains mainly C3 and C4, and which can be easily cracked to olefins, intermediate compounds, right? Other refinery off gases, like from catalytic and reforming operations, we get lot of off gases. That off gas can be further processed to derive various petrochemicals. Paraffinic and intermediate olefinic compound fractions are also used for petrochemical production. Hydrogen, which is used for ammonia production, that is also that may also present in the refinery of gases, and sulfur as a byproduct that is obtained from H2S by oxidation process. Now, hydroforming of the petrochemical stock, it produces benzene, toluene, xylene, that is called BTX, and it gives larger quantity of the hydrogen. Also, that is a feedstock, right? Naphtha feedstock or fuel oil, they accumulate in a larger quantity in the Indian refineries. So they are used to make various petrochemical product. Synthesis gas also we use, and catalytic reforming of that or partial combustion of that is also capable of giving petrochemical product. So petrochemical starting materials such as ethylene, acetylene, propylene, they are produced by steam cracking method. Petroleum coke, that is pure source of carbon for calcium carbide, acetylene, and or electrodes for aluminum industry, those are used. So this is the wide range of the feedstock those can be used for production of various petrochemical products. So moving forward, we will now discuss about the C1 chemicals that we can have, derived chemicals from C1. So that is methane. Methane we call CH4, right? So this is the methane. We can see that partial combustion, that is the major source. Partial combustion of the methane that gives, after combustion you will get the char, or char means carbon black. Okay. Now when it is pyrolyzed or pyrolysis is done, the methane is converted to hydrogen. It is also very huge useful source of other chemical reactions. And when methane is reacted with air, steam or oxygen, that means you are having hydrogen and carbon monoxide as a source, that is syngas. So syngas, you do steam gasification, you get hydrogen and carbon dioxide, right? So methane, again, it reacts with air, it forms hydrogen cyanide, HCN. Also, these are like methane. Now you can see from this hydrogen, it can be also used to produce ammonia. NH3 ammonia, it can be produced. So we need to add nitrogen plus hydrogen, it produces ammonia. You have to do the mass balance. Now again, this hydrogen is hugely highly used in ammonia production, right? This ammonia, it is again used with, it is reacted with air and it can also produce HCl. You can see from this flow chart that how this one from one chemical, this one methane C1 chemical, we get lot of product and usefulness in the other factory as well. So while we were this, so from this hydrogen and carbon dioxide, we can also separate the carbon dioxide. And this carbon dioxide reacts with ammonia. It produces urea. This ammonia again react with air. It produces nitric acid. This ammonia, okay, I already wrote here. And from this ammonia, it reacts with nitric acid. It forms ammonium nitrate. So here we got the hydrogen and carbon monoxide mixture, and that can be further used to produce the methanol. From the methanol we will get formaldehyde by oxidation. From methanol, hydrogen chloride, by acting with hydrogen chloride, we will get a list of chloromethanes. From reacting the methane with oxygen, we will get acetylene. This acetylene is useful to produce acryl nitrile. From this acetylene, we will also get chlorine alkalis, that is chloroethanes. Hydrogen chloride or acetic acid reacts with acetylene, it produces vinyl chloride or acetate. Also, acetylene. From acetylene, we get some dimers, and from that dimer reacts with HCl, it produces chloroprene. So from this chloromethanes, lot of extra chlorine, where we will get this chlorine also we get from other sources that reacts with methane, and it forms the chloromethane. So you get the overall idea that how um, one um, one chemical that is produced from one chemical reaction is used for another chemical reaction for another useful product. So thus we get a lot of range of petrochemical products from the crude, uh, from the feedstock of the petroleum industry refinery. So first we will discuss about methanol production. So there are two methods for methanol production. One is catalytic hydrogenation of the carbon monoxide, which produce 75% of the methanol. Another one is oxidation process of the liquefied petroleum gas, give the oxygenated hydrocarbon co-products, which of the methanol we get as a major fraction. So we will discuss now the main process that is highly used in the commercial level, that is catalytic hydrogenation of the carbon monoxide to produce methanol. So what are the chemical reactions involved in that process? So first we will get carbon monoxide. Hydrogenation, we will react with hydrogen and it will give methanol. And this is highly exothermic process around. So this is a straightforward reaction that you can see. Other than that, there are some side reactions. What are those? Carbon monoxide, it can act with different molar ratio with hydrogen. It forms methane again and water. It is also exothermic process. Another reaction in another mole ratio that will react, and it is also exothermic reaction. So side reaction to higher molecular compounds also may produce, like this way you are seeing that changing with the molar ratio, the products we are getting might be different, higher molecular weight. We get lot of alcohols and hydrocarbons. So you need to take care of the fact that this all is exothermic processes. Next we will discuss that how the methanol is produced from the syngas. What is syngas? This is nothing but mixture of carbon monoxide and hydrogen. So starting from syngas, that is carbon monoxide and hydrogen, here we are feeding this gas mixture as a hydrogen to carbon monoxide at a molar ratio of 2.25, which is obviously greater than the 12% greater than the theoretical value. We are giving at a 12% greater than the theoretical value, we are putting molar ratio of hydrogen and carbon monoxide at 2.25. Now, after the gas, it compressed. It is the compressor is compressed up to 3000 to 5000 psi. It got compressed, and it is then fed into a very high pressure converter, where the pressure is maintained 300 atmospheric condition. Also, the steam is being supplied, that is internal preheating is being done by the system to maintain the temperature of 300 to 375 degrees Celsius. Now, in the high pressure reactor or converter, it will convert this CO and carbon monoxide plus hydrogen into different mixture of methanol, um, heavy alcohols, heavy ends and other. So that will be further gone through the heat exchanger or condenser, where the 50% condensation per mass is been happening. Now it is passed through. Now the purge gas will be collected and some of the recycled is being done here to maintain the pressure. Now this stream is being uh, depressurized to it was very high pressure 350 atmosphere. It is pressured down to 14 atmosphere. Pressure is released, and then it is from flash drum is there. Here the flue gas will be escaped from the system, and crude methanol is further sent to the stir reactor, where KMnO4, this is nothing but permanganate, which is being used to remove the traces of ketones, aldehyde and others. From here, after refining, you get it to the ether tower, that is a stripper. From there, the top product will be collected ether, which is considered to be light end. It is first separated, and then the heavier is again fractionated or methanol tower. From here, the light end methanol will be collected from the above, and from the bottom the water is separated, and byproduct we get heavy alcohols. So for conversion, for this syngas to methanol conversion, we need to maintain this optimum condition. A 50% conversion per pass is at a optimum value of optimum parameter. Temperature equals to pressure equals to 240 atmosphere and temperature equals to 300 degrees Celsius. So this is how the syngas is converted to methanol in a high pressure reactor, and through series of stripper and fractionator we separated the methanol from the heavy ends. This optimum parameter need to be maintained. Next part is formaldehyde. In the formaldehyde production, there are two steps, two methods for producing formaldehyde from the methanol. First process is catalytic oxidation, that is oxidation and dehydrogenation of the methanol, and second process is oxidation of methane and or LPG to give oxygenated hydrocarbon co-products in which formaldehyde will be separated further. So we will discuss first the catalytic oxidation and dehydrogenation process. What are the chemical reactions involved? First happens oxidation process. So in the oxidation, the methanol is reacting with oxygen, which gives formaldehyde, which gives the formaldehyde and water. It is also an exothermic process. The next is after oxidation, pyrolysis is occurring, which is methanol. Directly, it can give formaldehyde and hydrogen, but this process is endothermic process. And other side reactions, or you can say complete conversion, is happening where methanol reacts with oxygen. It forms water plus CO2, which is also an exothermic process. It is highly exothermic process. So next is formaldehyde production that we will discuss through the flowchart process. Formaldehyde production from methanol. So it will be oxidation and dehydrogenation process. Let's discuss about this. This is the methanol, and see, we can have air from here. Preheated air is supplied by this line. So also it is compressed. So compressed, it preheated air at 0.2 atmosphere, and this methanol CH3OH, this methanol and this air is at ratio which is in the range of CH3OH and air, this ratio in the range of 30 to 50%. Okay, it should be maintained, and this ratio this molar ratio is very important for um, and also the temperature here very important. We will discuss further. So now in the methanol evaporator, the methanol vapor will be generated and that will feed to the catalytic reactor. In the catalytic reactor, the catalyst uses silver or copper gauge or their oxides. Okay. Now, after the catalytic conversion occurring, then the product will be taken. This is very high temperature condition is around here 450 to 600 degrees Celsius. Okay, so the heat is being recovered and then it is sent to the light end stripper. The lightings will be collected from the top of the stripper and it is scrubbed, water scrubbed, and then vent gases will be there and the dissolved chemicals will again come to the stripper, and from the bottom product it is sent to the alcohol stripper. From there, the methanol vapor is around 15% unreacted methanol will be there still, unreacted methanol that will be recycled back to the this point, and other which is converted, then that will be formaldehyde we will get as a 37% solution. So here one thing you need to understand, this methanol conversion, this methanol to formaldehyde production, this conversion is very catalyst specific. Suppose so we were discussing about this process of formaldehyde production from methanol. So this methanol formaldehyde production from the methanol is very catalyst specific, and where we see the recycling of the methanol is necessary because we get 15% unreacted methanol, right? So this process can be modified with another catalyst that will be further better. Another like we can use other of mixed oxide catalyst, molybdenum, iron, and this mixed catalyst that can give the 90% yield of the formaldehyde without a need of methanol to be recycled. Okay, and then this ratio, methanol to oxygen ratio, we keep it as 16 is to 1, and from there also there will be highly, that will be favorable for oxidation reaction. So by this modification in the process, we will get more yield of the formaldehyde out of the methanol. Temperature is a crucial factor, and also this ratio of methanol to oxygen, it is a crucial factor for deciding that how much unreacted methanol will be producing here, and that should be recycled to maximize the yield of formaldehyde. So next we will discuss about chloromethane production. So there are three so there are three methods for chloromethane production. First one is direct thermal methane chlorination process, which is very useful where there is direct substitution is occurring to produce the chloromethane, which is completely dependent on the molar ratio of methane and chlorine and their reaction condition. Chloromethane, by reactions of methanol and hydrochloric acid, which is kind of competitive and can be coupled with this methane chlorination process to use the byproduct HCl. Also, it reacts with CS2 and chlorine, and this is no longer economic condition. So we will now discuss the chemical reactions that how from methane we will get the chloromethane product. This whole lot of reaction involved in this process, those are highly exothermic in nature. So the first, what is happening here, that methane reacts with chlorine, it forms methyl chloride and HCl. This byproduct HCl we are getting. Then this further again react with chlorine. One more hydrogen is substituted and it produces dichloroethane, and then the substitution is straightforward. At last we will get Cl4 and HCl, so whole lot of HCl we get as a byproduct. So these all are exothermic reactions. So we will now discuss about the production of chloromethanes from methane. Earlier we have already told that the ratio of methane and chlorine and the reaction temperature is very essential to maintain this. As a result, this percentage, whatever percentage it will be produced, that will differ if we change those parameters initially. So here the methane we we mixed here with chlorine and send it to the reactor. Highly exothermic reactor, so we need to maintain the temperature inside the reactor. Some of the preheated feed we can take it out and premix here, mix here to maintain the temperature of the reactor. So from the reactor, the product is being taken out. So here we it is written that methane with or without nitrogen recycled for CCl4 dominant production. So from there we will get the mixture of dichloro di mixture of chloromethanes and other other fractions. So it will be first um, taken to the absorber where by the water it is washed. All the byproduct ACl will be cleared out. Then again it is sent to the neutralizer where 60% NaOH is used to again eliminate the ACl content, and then it is taken to the it compressed and then it is taken to the partial decondenser and then drying tower. Drying is being done by using 98% H2SO4 acid, and spent H2SO4 can be used another form. Anyways, the gas can be further sent to the recycling part. Okay, now the chloromethane product, the recovered chlorides from this end, is further sent to the fractionator where it is fractionated based upon the molecular weight and all. So it is fractionated. So these light ends can be further chlorinated in another reactor if the nitrogen recycle is not used. So in this chloromethane production, one thing is very essential, that is to control the reaction happening inside the reactor. That is the concerning factor. So here, as we already discussed, that all the chain reactions, these are highly exothermic in nature, and those are propagated by involving the chlorine radicals, right? And that can be explosive if it is not controlled. The temperature is not controlled here. So the mole ratio is also important. So it was the mole So here there was a scale of mole ratio, like this kind of scale of mole ratio of chlorine and CH4. Okay, so 0, 2, 4, 6, 10, 12, 14, 16, 18, like that. Okay, so the range is, this range is zone 1, this range is zone 2, this one is zone 3, and this one is zone 4. So in this region, if your in this region, if your process is condition is aligning, then it is controlled reaction is occurring. But in this reaction, it is uncontrolled reaction. So you can see that how important this molar ratio for happening this reaction. And also 3, we will get detonation condition. So what are the methods that can be used to control the reactions that is occurring in the process 1, region 1? Use a methane cycle where there is considerable excess of methane. This can give largely mono and dichloromethane product, but increases methane cycle and difficulty of the product separation will be there. Otherwise, you can use the diluent gas like nitrogen and other product gases you can use, or you can use the liquid co-solvent as well. Add chlorine in a stage wise along the reactor, not at a time, and design the reactor for high velocity isothermal operation at a relatively expensive method, that can control the unwanted or uncontrolled reaction occurring in the reactor. Temperature should be maintained and this molar ratio should be maintained properly. So then the next one is production of the ethylene and acetylene. That is also a very useful product out of the petrochemical industry. So this ethylene and acetylene, these olefins and alkenes, are formed by catalytic cracking of various low molecular weight hydrocarbons in the intermediate product. In catalytic cracking process, ethylene, propylene, butadiene, aromatics are formed as products. So the most important carbon 2 or C2 petrochemical products we will be discussing as ethylene and acetylene. Now the ethylene can be produced from 2-3 methods. One is fermentation of alcohol. We can produce ethylene, or it can be produced from refinery off gases or hydrocarbon steam cracking, which is widely used. Other acetylene can be produced by calcium carbide, partial oxidation of the petroleum fractions, hydrocarbon steam cracking process. Now the steam cracking process, they produces ethylene or acetylene in the ratio of 0.3 to 2, also depending on the operating conditions. So we will now discuss what are the chemical reactions involved in the steam cracking process of the petroleum hydrocarbon. So this is kind of complex reaction or series of other lot of product are generating. So we will discuss. Suppose this is a common hydrocarbon feed. It is a uh, steam cracking process which is optional. Very high temperature 700 to 800 degrees Celsius. It is primarily produced ethylene 4 to 15% it will produce. It produce ethane, acetylene 7 to 13%. It also produces hydrogen a lot amount 25 to 30%, carbon dioxide, carbon monoxide, methane, propane, propylene, butane, butylene, carbon, and other heavy fractions. So we can see these lot of chemicals we are getting from from this steam cracking process of the petroleum hydrocarbons, right? So it is very useful technique, steam cracking process, to produce lot of chemicals at once. We will now thoroughly discuss about acetylene and ethylene production by steam cracking process through this uh, flowchart. So here we are getting that naphtha as a feedstock from the petroleum refinery. We are mixing with excess steam. Also, the fuel is being sent to maintain the temperature. Pyrolysis is occurring, so we need to maintain this high temperature by this fuel. Excess steam can be collected, and the product is sent to the uh, flash drum where steam is separated, and the rest of the thing is oil is scrubbed, waste oil is collected, and then it is compressed at 35 megapascal. Flash drum by flash drum, it is taken to the washer where it is anyway solution is being washed to Then after drying, the C1 and C1 to C3 is sent to the demethanizer. From that, methane and other tail gas is separated, and the heavier fraction C2 and C3 is sent to the deethanizer, where again the C2 is being separated and that is sent to the C2 splitter. Because this is C2, it has lot of 2 carbon containing compounds, so that is sent to the C2 splitter. From there it is at the light end of ethylene acetylene we will get, and this C3 compound we are getting, that is fed to the uh, debutanizer. This is the complex mixture, so it is sent, and the butanizer, depropanizer, and C3 splitter, those are separated and can be recycled as C2, C3, C4 saturates in a separate furnace, pyrolysis furnace. So from here at the top we will get the propylene as a product, similarly aromatics as a product, butadiene as a product. Here we got the acetylene and ethylene. If we don't want acetylene, then it will be uh, a optional route is there, that it is hydrogenated and it forms the acetylene converter. So all of the thing acetylene will be collected and that will be stripper. From extracting solvent, it will separate the acetylene. So there are few products. Suppose this ethylene, propylene, aromatics, butadiene, acetylene. These all products we are getting from this steam cracking of uh, hydrocarbons. So we can previously we have discussed the other petrochemicals that we can derive from the methane. Similarly, you can see this is whole lot of petrochemicals that we can derive from the ethylene feedstock by various chemical reactions, right? So this ethylene as a feedstock, that is we can get from the refinery cracked gas or cracking of the ethane propane, we get ethylene. So ethylene, it can be act as a catalyst. From the ethylene we can get polyethylene by polymeric reaction. Ethylene um, reacted with oxygen, acetic acid and presence of catalyst, we will get vinyl acetate. Ethylene, oxygen presence, catalyst, it form ethylene oxide. From that ethylene oxide, we in presence of ammonia, it is producing ethanol amines that we will discuss further. Ethylene oxide reacted with water, it form ethylene glycol. Polyglycol also produced, diethylene glycol it can be. So ethylene reacted with hypochlorous acid, it forms ethylene chlorohydrin. Reacted with alkali, it forms ethylene oxide. Ethylene oxide dehydrogenation process, it produced in the presence of hydrogen cyanide, it produces acryl nitrile. From the ethylene chlorination, it produces ethylene dichloride. Hydrogen chloride can be taken out and we will get vinyl chloride. Ethylene in presence of the bromine, it forms ethylene dibromide. Presence of the hydrogen chloride, it produces ethyl chloride. In presence of the water and presence of the catalyst, it produces ethyl alcohol, and from that we can also produce acetaldehyde. In the presence of the sulfuric acid, it forms sulfuric esters, and in water dissolved, it can be produced ethyl alcohol. Ethylene reacts with the benzene, it forms ethyl benzene, and from there it produces styrene. So you can see a lot of petrochemical product which we can synthesize from the feedstock of ethylene. The next we will be discussing about the production of ethylene dichloride or 1,2-dichloroethane. What are the methods of production? There are three methods you can consider: ethylene and chlorine reaction in liquid phase or vapor phase, byproduct of direct chlorination of ethane to ethyl chloride, and byproduct of chlorinated hydrocarbons. So the main reaction involved in ethylene dichloride formation via reaction of ethylene and chlorine. This is very straightforward. That is, ethylene, it reacts with chlorine and it forms ethylene dichloride. The process reaction involving this is very simple, and we will now discuss through the flow sheet that how ethylene dichloride is it is formed via ethylene and chlorine as a feedstock. So you can see that ethylene and chlorine are mixed and those are in the liquid phase reaction, those are bubbled up. So here the catalyst is used FeCl3 or ethylene bromide as a catalyst, ferric chloride or ethylene bromide as a catalyst. So it is bubbled up, and the product will be taken to the uh, there is two phase, gas phase and liquid phase. So the gas phase is taken to the scrubbing unit where HCl is being scrubbed using 8 to 6 to 8% of NaOH solution, and the undissolved compounds like hydrogen, methane, ethane, ethylene, that will be taken to the off gas, and another one will be wash. The liquid product, it is again washed via acid wash, again 6 to 8% of the NaOH in the stir tank reactor, and then the crude is being fractionated. From there you will get ethylene dichloride as a top product and heavy products at the bottom of the fractionator. Very simple, straightforward reaction, nothing complicated in this. The next one is vinyl chloride, that is CH2CHCl, right? Vinyl chloride. The method of production is ethylene dichloride thermal pyrolysis, acetylene and HCl reaction, ethylene dichloride caustic reaction. So we will be focusing on the thermal pyrolysis process. So what are the chemical reactions involved? That is also straightforward. That is ethylene dichloride that we formed earlier. It is pyrolyzed at a higher temperature pressure condition and it forms vinyl chloride and byproduct at HCl. Let's discuss about the process flowchart. So in this process flowchart, sorry for my uh, voice is broken today. This ethylene dichloride from the storage, it is vaporized and sent to the dryer or that for removing the moisture, and then it is sent to the pyrolysis furnace. It is at temperature of 500 degrees Celsius, 4 atmospheric pressure, and from the tubular, these are from this ethylene dichloride will be sent. Okay, and to maintain this high temperature we are using the flue gas that will be sent to the shell site. Tube site, this ethylene dichloride will pass, and shell site the flue gas will pass. Okay, now from the product that will be sent to the immediate quencher. For after quenching, the liquid product will be taken to the vinyl steel. From that, the vinyl chloride will be collected as a top product, and the heavy end will be sent to the EDC, ethylene dichloride steel, and from there, it is some vapor will form, and that vapor will recycle at this point where it is like this. From this, it is by steam it is vaporized, and recycled vapor can be used further for more maximizing the yield, and then some of the ethylene dichloride quench can be recycled to use at this point. Okay, next one is ethanolamines. So we have already So we have already seen that ethanolamine can be a great solvent to remove the acid gases like CO2, very uh, CO2 philic solvent that industrially it is used for CO2 capture. So the examples are mono ethanolamine, di and triethanolamine. What are the methods of production? That is ethylene dichloride, thermal pyrolysis, that is they produce ethanolamine, acetylene and HCl reaction, ethylene dichloride caustic reaction. So the reactions involved, that is very complex set of reactions, like it reacts with ethylene oxide. It first react with ammonia. It produced monoethanolamine. Okay, and then again ethylene oxide plus monoethanolamine, it reacts with and it forms diethanolamine. Again ethylene oxide, it reacts with diethanolamine and it forms triethanolamine. So these products ratios depend on the conditions also. So this is very important for a complex set of reactions. The next one is simple. This is very simple flow sheet. This ammonia and ethylene oxide are the main two reactant, and it is maintained as 20 to 30% of aqueous solution. It is fed to the stir tank reactor, where the water jacketed cooling system should be there to maintain the temperature of the reactor. The top product will be collected for ammonia flash, because ammonia converting of ammonia, it's not a very easy process, so it will be unreacted some of the part, and then it can be recycled back to this feed point. And then the liquid and these fractions can be this crude ethanolamines can be separated. Water separation tower is there, water is separated, then particularly three towers will be there for separating the monoethanolamine, diethanolamine and triethanolamine as a top product. And at the end there will be heavy ends at the third stage of the stripper. So these I have focused on mostly the used chemicals, petrochemicals. There are a lot of other petrochemicals present. That's it for today's class. There is lot of other petrochemical products are also present throughout the other chemical reactions that is not possible to cover within this short period of one lecture, but we will be discussing some of the other petrochemical maybe in the next class. Till then, if there is any query, then you can ask directly in the portal, NPTEL portal, and we will meet in the next class following up some of the other petrochemical processes. Coming Friday, we will meet. Thanks. We will end this session today now. Thank you.